I think we can start, ma'am.
Yeah, sure.
So welcome, Professor Raju, sir. This will be an interactive session and people can ask their questions regarding dielectric permittivity, polarization, breakdown of gases, solids. So, Dr. Gaur Govinda Raju obtained the B Engineering degree in electrical engineering from the University of Bangalore, India, and PhD degree from the University of Liverpool, UK. He was awarded Leverhulme Scholarship and Leverhulme Travel Bursary during doctoral studies. He then worked in the research laboratories of Associated Electrical Industries, UK. He joined the Department of High Voltage Engineering in IISc Bangalore and became its head during 1975 to 1980. Concurrently, he held the Commonwealth Fellowship and visiting lectureship in the University of Sheffield during 1972-73 and 74-75. He joined the University of Windsor, Ontario, Canada in 1980 as professor and became the head of the Department of Electrical Engineering during 1989 to 1997 and again in 2000 to 2002. He is currently an emeritus professor at the University of Windsor. He has published over 140 research papers in 3 books. He is registered professional engineer and fellow of the Institute of Engineers, India. So we are glad to have you, sir. And we can start the session.
Kinshuk, we can start with some of the questions that our group had.
Yeah, sure. So we'll begin with, we will just look at the questions.
So Professor Raju, by that time we are having the discussion, I'd like to tell you that I am Alok Ranjan Verma. I joined the IIT Kanpur as an assistant professor. So I'm really glad to have you here. I did my PhD from IISc Bangalore. So I've heard your name and gone through your books. So it is really pleasure having you here in the early morning, as said. So glad, and it's really going to be a good, session with your wonderful experience and the discussion which you are going to share, or the knowledge which you are going to share with us. Thank you for being here, sir.
Thank you so much.
Professor Raju, this morning we had a discussion on polarization and we talked about the various relaxation times and various polarization processes. I remember asking you before that depending upon the time constants of the various relaxation processes, would it be more meaningful to model dielectrics as a single RC circuit or as a combination of several RC circuits? Maybe you can start with a discussion on that while we wait for the other questions.
Sure. If one looks at a curve of polarizability as a function of frequency, starting from the left-hand side, which is the highest frequency, you get the optical frequency where the electronic polarization takes place. The electronic polarization is the displacement of the electron cloud with respect to the nucleus of the same atom. And therefore, every atom will have an electronic polarization. It is the structure of the atom which gives rise to this polarization. Now, at a lower frequency, which is the atomic polarizability, we have 10 to the 13 to 10 to the 14 hertz. And this is where the displacement of the two atoms in a molecule takes place. Moving to the right-hand side, we have then the dipolar polarizability. The dipolar polarizability arises due to the fact that there is a difference in the electronegativity of the two atoms, which two or more atoms, which constitute the molecule. For example, a hydrogen molecule cannot have a dipolar polarizability because both atoms have the same electronegativity. But if you take an atom like, if you take a molecule like HCl, then the chlorine is more electronegative than hydrogen, and therefore the hydrogen atom tends to attract a little more negative charge towards it, and there will be a dipole moment induced in the atom. Now, this occurs only in an electric field. As soon as you remove the electric field, the dipolar polarizability goes to zero. Whereas if you remove the electric field actually has no influence on the optical or electronic polarizability. In that high frequency range, we call it absorption rather than dielectric loss. Now, from the dipolar polarizability could be anywhere from 10 to the power of 11 hertz to as low as 10 kilohertz, 10 to the 4 hertz. In a polymer, the dipolar polarizability arises due to various reasons, including the small branches of the dipolar chain. Now, the chain may be dissociated, or it may just twist, or it may rotate, and it may have different kinds of motion. That is where the relaxation time, each process will have a relaxation time of its own. Now, since so many things can happen in a polymer, the relaxation will not be individual values. It may be a continuous change of the polarizability, and this is when you have to have a distributed relaxation time. Now, the distribution relaxation time, we need to have, what do we mean by the distribution relaxation time? It is the distribution of the various values around a mean value. Now, what kind of a distribution would we have? In the previous talk, I said it's Maxwellian distribution. Actually, what I meant was it could be a Gaussian distribution. Now, if it is a Gaussian distribution, then you can have the distribution as a function of the parameters. Moving still to the right-hand side forward, there we have interfacial polarization, where you have the frequency range from 1 second to probably the lower frequencies of up to 10 to the minus 5 or 10 to the minus 6 seconds. So this is the time range of the polarizability, various polarization mechanisms. Now, if you wish to represent the dielectric, first of all, you have to choose in which range of this frequency the material shows the relaxation mechanism, because not all of them will be available will be present in all the materials. If the frequency of interest is of engineering for us, probably it would be 50 or 60 hertz, and probably the DC polarizability, which is and the AC, which is the optical, if you want, 10 to the 16 hertz. So after you decide which range of frequency you want to model, you must decide what kind of distribution you are looking for. Are you looking for a mean value, a single value, or are you looking for the range of all the values in which the dielectric constant could lie? The modeling itself, it will decide what is it you want from the whole spectrum of the material.
Thank you. That was a very illuminating answer. King Shuk, you want to ask some questions which you have from the participants?
Sure.
Our participants asked some questions. So I will start with a basic one. Sendil Kumar asked, I am not much familiar about polarization. Can you please explain what is polarization and depolarization time and how it is related to breakdown strength of a dielectric material?
Polarization is a phenomenon where each molecule or each atom is the charges of the atom or the molecule are displaced with respect to the nucleus. And therefore, it would have what we call a dipole moment. The most fundamental definition of a dipole moment is two charges separated by a small distance d, let us say. Then the dipole moment is the product of the charge and the distance between the two charges. And it is a vector quantity, of course. The dipole moment is always taken to be from the negative charge to the positive charge. Therefore, in an electric field, the negative end would point towards the positive electrode, and the other end would appropriately at the opposite end. So this is the basic dipole moment of a molecule. If you take a material, then you will have many molecules there per centimeter cube. If it is a solid, you would have something like 10 to the 22 or 10 to the power of 23 molecules per centimeter cube. So there would be an average dipole moment, because not all molecules experience the same electric field. The molecules are all oriented in a different direction before the electric field was applied, and therefore the torque they experience will depend upon at which angle it was situated when the applied electric field was applied. Therefore, you would have an average value, and this average value would be called the polarization per unit volume, per centimeter cube or per centimeter cube or whatever. So what are the reasons for which the two ends of the molecule will orient in an electric field? This is the polarization mechanism. Now, in an alternating field, of course, you will have to take into account the fact that the molecule, every half a cycle, the force it experiences changes the direction. And also the torque it experiences will depend upon the angle it is situated with respect to the electric field. Therefore, taking these things into account, if you trace the history of the dielectric theory, the very first theory was called Clausius-Mossetti equation, where you have on the right-hand side the dielectric constant, which is a measurable quantity. And on the right-hand side, you would have the equation would contain the dipole moment, which is the basic fundamental parameter that goes that controls the value of the dielectric constant. And therefore, the theory always tries to relate what is measurable and what are the basic fundamental parameters of the atom or the molecule. The state of the material, whether it's a gas or a liquid and so on, it's controllable by the experiment. But the dipole moment itself, we don't have a lot of tools to change the dipole moment. To change the dipole moment, you will have to change the molecule itself. Then it becomes a new material. So the polarization theories from the Clausius-Mossotti. The Clausius-Mossotti equation assumes that the electric field applied is the same within the dielectric tube, except for the dielectric constant. But it is not so. It was soon realized that the measured values did not agree with the calculated values, and therefore what is known as an internal field exists. Now, the internal field exists because every dipole is surrounded by other dipoles, and they are also charged units, and therefore they change the electric field. And this electric field is called the internal field. The Clausius-Mossotti equation, which was improved, it improved by theory by Debye. In the Clausius-Mossotti equation, there is no parameter which has temperature. Therefore, it assumes that the dielectric constant is not dependent on the temperature. But when we make measurements, the temperature comes into picture. So this was taken into account by Debye, I think 1904 or somewhere over there. And he gave the Debye theory, which has the dipole moment and the temperature and the electric field, of course, into account. What he did was he found out, or he calculated mathematically what is the fraction of the molecules that experience a component of the electric field. Not all, as I said, molecules experience the same force. Now, from there, the Debye theory does not take into account the internal field. Therefore, Onsager developed it further, and then Kirkwood and so on. And in the meantime, the statistical treatment also gave rise to a slightly different branch of dielectric theory. That, in concise, is what the dielectric theory about. Now, all this is with considering the molecule, and it calculates the dielectric constant as a function of dipole moment. On the other hand, these are all frequency domain measurements. On the other hand, you can also, people observe when you apply a voltage, the current varies as a function of time. And therefore, the time dependence of the current that flows through is the time gave rise to the time domain spectroscopy, where you take the current as a function of time, and then you apply the Fourier or Laplace transform, and you obtain the experimental value. The struggle for theory people and the experimental people is to obtain agreement between the time domain and the experimental frequency domain values. That, as I understand it, is the essence of all dipole theory. Now, this is, of course, at low electric field. When you apply a higher electric field, other things come into picture. The conduction of the electron, the difference between the valence band and the conduction band, and so on. There you have 4 or 5 theories to apply in order to understand the field dependence of the current, whether it is proportional to the electric field or whether it is proportional to e to the power of half and so on. And if you apply a still higher field, of course, the breakdown theory takes place. There again, you have a wide variety. One is the intrinsic electric field, intrinsic dielectric strength. Now, the intrinsic dielectric strength is purely due to electronic structure of the material. It is controlled by the electrons and ions within the material. But this is very difficult to obtain, particularly for non-homogeneous materials. Now, the intrinsic dielectric field may be a few 100 microns. If you exceed the thickness, you rapidly reach the range of the extrinsic breakdown strength, which is what most engineers experience when they do the experiment, even if the thickness is of a tape, for example. A tape which has got half a millimeter thick or 0.1 millimeter thick, most probably it would be an extrinsic breakdown strength. But that is what is of importance for us, and therefore we always measure more or less either as a function of temperature or both as a function of temperature and electric field, the extrinsic field strength. That, in a sense, boils down the dielectric theory. And of course, during the past 10 years, we have a new type of material, which is the nanomaterials, where Professor Gupta has made so many valuable contributions. I'm sorry, the answer is always usually longer than the question.
But it is wonderful the way you have encapsulated the entire theory in such a short time. I mean, in such a short answer, you've given us the essence of both polarization as well as breakdown. So it's really wonderful. Yes, there are some more questions.
Sir, I myself would like to know that since intrinsic breakdown is perhaps not achievable practically, how do we really know what is the intrinsic breakdown strength in laboratory or in any practical way?
Yeah, you cannot measure the intrinsic breakdown strength, for example, PTFE. In order to obtain the electric field strength, first you will have to make sure that the breakdown is entirely due to the motion of electrons and ions as in a gas. Now, gas always has intrinsic, it's easier to measure the dielectric intrinsic field strength in a gas, but not in a solid. And therefore, it is almost impossible to measure the intrinsic field strength unless you produce PTFE tape of 100 micrometer thick. But such a film would have no engineering applications. So one would not want to spend so much time in measuring the intrinsic field strength when it has no practical value. What is required is what voltage it can withstand in a practical application. So you only measure the extrinsic field strength. Why would you want to measure the intrinsic field strength when it has no value in the design? That is the question.
Yeah, okay. Thank you, sir. So we have several questions from Narasimha Rao. So if you can unmute yourself, you can ask the questions directly. Can you unmute yourself?
You should ask the question yourself.
I will ask the questions.
There might be confusion.
Yeah. He asked the effect of polarization at high frequency.
The essence of polarization at high frequency, as I said, if you view the atom or the molecule, the behavior would be quite different. If you take an atom, for example, which is the simplest to understand, a hydrogen or a helium atom, it has got only electrons and the nucleus. And when you apply the electric field, the electronic charge would oscillate about the nucleus depending upon which electrode has the positive polarity and the negative polarity. Now, at high frequency, it depends what range you are talking about. If the high frequency is megahertz range, then a different mechanism applies. If the high frequency is only in the atomic frequency range, 10 to the 11 to 10 to the 13 hertz, then the polarizability would be, of course, less, and the influence of the field would not be as much as in a dipolar. polarizability. Now, at high frequency range, let us take only the orientational polarization. At one end, you have got, I always talk about water because that is the one which is closest to the Debye theory. And so when I say water, you can take it as a perfectly modeled molecule. Now in water, we have a frequency of gigahertz, whereas in a polymer, you may get a frequency at 1 megahertz itself. So that is the behavior of the material. And the dielectric constant, the two components of the dielectric constant, one is the real part and the other one is the imaginary part, loss factor, we call it in engineering. Now that, of course, depends upon what shape what kind of relaxation is taking place. In a simple Debye theory, you have a semicircle, whereas in other theories, you get different kinds of relaxation frequency, and therefore the shape of the two plots, epsilon double prime versus epsilon prime, will change from molecule to molecule, and obtaining the relaxation time itself would not be such an easy experimental task.
He also asks about the effect of polarization at sine wave and square waveforms.
Yes, in square wave waveform, you will have to break it into Fourier series. And then it is a superimposition of a Fourier series, and therefore for each frequency, you will have to calculate the corresponding response and try to find a way of adding it up. Because the two are the vector quantities. So you will have to find an intelligent way of adding up for a square wave.
His third question is not very clear to me. He just writes how to cause polarization breakdown in thin films. I didn't get the question that he asked. So if you can't unmute yourself, I think we can skip it.
Yeah, I think we can go on to the next question.
Yeah. Jacob asks, can we directly relate polarization value and permittivity, or is it a material property which varies with various material?
Yeah. Can you repeat it a bit slow, please?
He asks about the relation between polarization and permittivity.
Polarization is the atomic and molecular properties. Permittivity is measurable property. So by obtaining the measured quantity, we want to arrive at the atomic and molecular properties of the molecule or the atom. So you will see that in the dielectric theories, on the one hand side, you will have dielectric constant. On the other side, you will have the dipole moment and the applied electric field and the temperature at which the measurement was carried out. For example, the Debye theory says on the left-hand side, you have epsilon minus 1 over epsilon plus 2. This we call it as molar polarizability. Now on the right-hand side, the parameters that appears is it's n mu squared over 9 kT, where n is the number of molecules per meter cube or centimeter cube, which is obtained by the density of the material. Mu is the dipole moment, which depends upon the charge distribution, it is not that easy to get. Actually, mu is obtained by calculating the dielectric constant. N mu squared 9, K is of course the Boltzmann constant, and T is the temperature and an electric field. So the relation between polarization and dipole moment is the essence of the dielectric theory at low electric fields.
Sir, I have a related question on this.
I could say here, because there is a reference to the ferroelectricity in the talk. Now, if you see that equation, on the right-hand side, you have N mu squared over 9KT. So all parameters except T are constant for a given material. And therefore, you can put it as a constant value. So you have, if you call that constant value T sub C, which is a critical temperature or a Curie temperature, then on the right-hand side, you have Tc by T. And that, when it becomes 1, on one side of the temperature, you have the material having a very high dielectric constant. On the other side, you have got the low dielectric constant, and therefore there's a peak in the dielectric constant. This is what we call ferroelectricity in correspondence with ferromagnetism. So this kind of equation for Onsager equation is more complicated and so on.
So who was asking some question? Vinit, was it?
No, I was Qasim.
Oh, okay.
So I was asking, sir. Sir, my question is a very theoretical one. So sometimes we need to give, for example, in modeling, so in COMSOL modeling, we need to give permittivity value, some permittivity value to a conductor. So basically, it does not mean anything, but what should we give? What I have seen that if we give the permittivity value of conductor as 1, and if we give the permittivity value as very high value, both the results remain the same. So in your view, which one is better? So basically, this is a theoretical question. So
see, permittivity at in vacuum it is 1.
Yes, sir.
With when you insert a material there, it maybe 4 or 10 or 80 or whatever it is, depending upon the material you have. As the conductivity increases, the permittivity increases. Therefore, I cannot figure out an equation where the dielectric value can be 1 and 10,000, and you get the same result.
This is probably a construct of the software that you are using, which is not the right. I don't think Professor Raju is the right person to ask about the nitty-gritties of a commercial software.
But sir, if you
unless of course, unless of course the function of epsilon double prime, I mean, what quantity you are getting the same thing when you apply epsilon is equal to 1 and epsilon is equal to say 10 to the 6. You said so we get the same result.
Distribution plot, I always got the same. So in metal, there will be no electric field. Yes, sir. So in both the cases, it happens.
When you say you get the same result,
yes,
same
sir.
Result of what?
So
electric breakdown voltage?
No, sir. For example, electric field.
You apply the electric field. See a material.
Electric field distribution means inside the geometry of whatever we are modeling. So if we want to plot the electric field distribution, so we will always get the similar type of distribution, or not similar but same type of distribution. If we give the permittivity of metal as 1, or dielectric constant of metal as 1, and as well as if the dielectric constant of metal is given at very high value, for example 1000, 2000, then also the electric field distribution at every point will be same.
That means the field within the material is highly non-uniform. If you take the field of a point plane gap, for example, at close to the point, the field would be very high, but far away from the point, irrespective of what material is there, you would still get a distribution where the field is very low. And therefore, I would expect that if you are getting the same value when epsilon is equal to 1 for vacuum and epsilon 10 to the 5 for the highly conducting material, if the field is the same, then I would say it has a very non-uniform distribution within the material. And that's why the dielectric constant is not making any difference to your field calculator. Because no matter what the dielectric constant is there, if you had a piece of polythene, or if you had a piece of ferroelectric material, the two differ by 2 or 3 orders of magnitude in the dielectric constant. But still, the field near the plate electrode for both materials would be more or less the same. So you are getting the same electric field irrespective of the dielectric constant. So I would say it points to the fact that the field is highly non-uniform and you cannot apply the field the same at every point within the dielectric.
Okay, sir.
Does that make sense?
Yes, sir, because that was a very theoretical question, so I think it makes sense. Yes, sir.
Yeah, good.
We have a question from Ritanjali. She asked how polarization occurs in nanocomposites.
I think Professor Gupta can answer that better than I can do. Because there are 2 or 3 theories for the nanomaterial. I think I will have to look up the book to find out which one is more applicable. The macroscopic theories are not applicable for nanomaterial. That much is known.
So as you say, Professor Raju, that we cannot actually change the dipole moments. We don't have it in our control. So I think ultimately when people are working in nanodielectrics, that is what they're actually trying to do. They're trying to incorporate fillers and they're trying to affect the dielectricity at the nanometric level, which is what we should be able to do, but we're not still in a position to do. So yeah, we'll have to wait and see. We're still in a position where we are trying to find out what is happening. Once we know what is actually happening due to the incorporation of nanofillers, maybe we will be in a position where we can actually tailor the nanofillers in such a way that the dielectricity can be affected and therefore the permittivity can be what we want it to be. But Ritanjali, we will have a question. We will have a session on functionally graded materials where we do tailor the permittivity to a certain extent. This will be by Professor S.A. Kasim. I think it is tomorrow, right?
Yes.
Yeah.
Yes.
Yeah. So you can attend that talk.
She also asked how to define interface in composite films.
How to?
Define interface in composite films.
The interface is, it depends on the way you manufacture the sample. For example, interface could be between atomic or molecular layers where you don't have much control over the thickness between the interface, or interface between two tapes, one wound over the other. Now, in the macroscopic sample where the thickness is controllable, the interface, of course, depends upon the dielectric constant and the conductivity of the different layers. And one tries to get as uniform field as possible in case of cables and geometries of that type. But in case of parallel plane arrangements, the interface between two tapes, it's easy enough to calculate from the dielectric constant of the material. But at nano level, it's a lot more difficult, as Professor Gupta just now said.
Yeah, we have another question from Sendil. He asks that polymer will have some dielectric value and nanoparticles normally have some dielectric value. My question is about polymer composites. How the dielectric properties get altered and how will the dielectric value in the interface region get altered? Is there any possible method to measure it?
You can measure the aggregate polymerization mechanism. But again, in order to separate out, you will have to choose, you will have to make a measurement over the wide range at all frequencies, and then apply the criterion I mentioned earlier, depending upon at which frequency range you are observing that relaxation frequency, which frequency you are getting the peak, you must arrive at whether it is dipolar or whether it is atomic polarizability and so on. Now, for example, in the epoxy resin samples, which has been studied extensively in Kanpur, we find that it is not possible to exclusively say this is due to interfacial polarization, except at the point where you put the electrodes. Between the electrode and the sample, no matter how much you try, the junction cannot be made perfect because you are changing the medium from conducting medium to an insulating medium. The most common way of is to vacuum coat the sample on both sides so that between the electrode and the dielectric, there would not be insulating voids. But although that is the as close to perfect junction as you can think of, because then you can say that there is no electric field within the triple junction. There is no way you can make out simply by looking at the dielectric constant and say, well, this is due to interfacial polarization. You must have the frequency dependence in order to even make a approximate intelligent guess. Now, this is what the time domain spectroscopy gives you. Because by a single measurement of the current as a function of time, you can obtain the dielectric constant at various frequencies. And then you can say, oh, this is probably due to permanent dipole moment. Now, if it is a permanent dipole moment, let us see how the polarizability varies with the function of temperature. And then you can look at the ingredients and say, Is there an oxygen? Is there a chlorine? Or these highly electronegative atoms? There would be, surely. Therefore, you can begin to understand which component is acting.
Do it in maximum. Do it in maximum.
May I request all the participants who are not speaking to keep their mics muted?
Yeah, Ashok Narayan, your mic is getting unmuted automatically, perhaps, or whatever, it's fluctuating. So next we have an interesting question. It's from Niharika Borua. She asks that, as I have seen in some literature, the frequency domain spectroscopy for XLP at different aging temperatures for dielectric constant show different trends. For example, at 100 degrees centigrade, thermal aging dielectric constant values decreases with aging durations. However, at 120 degrees centigrade, the reverse happens. How does the aging temperature affects the dielectric constants? And she also has a follow-up question. Is there any particular temperature limit for a specific dielectric above which the trend line reverses in nature? Sir, you are muted. Sir?
Professor Raju, you're muted. We can't hear you. You'll have to unmute yourself. Yeah.
What about now?
Yeah, now we are good.
Yeah. The question on temperature is easy enough to answer. In all polymers, you have the melting point. Before the melting point, you have got the gas transition temperature. And at that point, you can expect the molecules to be mobile because it is reaching the fluid state. So at that point, if you reach that point, the values beyond that temperature don't have much meaning because you no longer have the solid you started with. So that is the second part of the question. And the first part of the question was at some temperature, the dielectric constant reaches a peak and decreases the value. I would say like to look at the ferroelectric behavior. Is there a ferroelectric type of behavior taking place where the dielectric constant increases and at a particular temperature it begins to decrease? It may not be exactly a ferroelectric material as we understand, but within the bulk, there may be some phenomena taking place corresponding to that. At the local temperature within the bulk material, is something happening that will tell us that the dielectric molecules are in some kind of a, not bound to the lattice, but somehow free from the lattice, and therefore the dielectric constant can show a reverse trend.
So this morning there was a question that students who were trying to do frequency domain spectroscopy, they complained that when they wanted to look at 10 to the power minus 4 values, I mean polarization mechanisms at 10 to the power minus 4 hertz, they had to wait a very long time and they wanted a solution to that. Would you say that time domain spectroscopy would kind of reduce their agony?
Yeah, sure. We have for frequency less than 1 hertz, even 0.1, maybe 0.5 hertz. I would be very cautious in applying the frequency domain values because you would be waiting for days together to attain a steady value of the. But the time domain spectroscopy is the best for frequency lower than 1 hertz. But there it's much better to measure the current, and you apply the transformation rather than taking the value which the second meter in the instrument shows. In fact, in many exhibitions where they show this, our instrument is the best. If you ask what kind of transformation did you apply, in most cases, they would not even know that there was a transformation involved from time domain to frequency domain. They say the instrument shows everything and you don't have to do anything at all, which is part of totally anti-negative to the thesis that students must know how to do it, because they would be designing such equipments in future. I always tell my students to obtain the transformation themselves. And then they will know at what point they will have to obtain this, what relaxation mechanism is taking place.
No, Kinshuk, it's not happening. Wait.
It's more.
Yeah, can you hear me?
Yeah.
So we have questions with us, but we would like to tell the participants that if they want to ask questions, they can unmute themselves and ask their questions also.
No, they will have to raise their hands and then we can unmute them. Go ahead, Kinshuk.
Yeah, so we have a question from Romana Jafar. Interfacial polarization, she wants to know about interfacial polarization in nanodielectrics or nanocomposite. I think it's a repeated question.
Well, first of all, the interfacial polarization must define the two components well, and only then you can think of the effect of interfacial polarization when the two come in series or when the two come in parallel. Now, in the case of a nanomaterial, or the material, the grain size, and the not only the interatomic distance between one particle and the other particle of a different kind, but what is the fraction of either sample. That means the interface, the distance between the two atoms of the same kind. Yeah. Usually what happens is the percentage mixture is quite so small. You put the 8%, 9%, like that. So the neighboring atom would be the major component. But there's also certain influence of the particle of the same kind, which is at another point, which is far away, several molecules away. So that is where the percentage of the component comes into picture. So these two information you should have before you apply an interfacial polarization for a nanomaterial.
So Dr. Elan has asked, could you throw light on polarization and space charge accumulation in the dielectric under electrical stress?
Yes, that That is an important aspect. The space charge occurs at a high electric field, or when the mobility is very low. The high electric field space charge effect is influenced by the charges injected into the material due to the electric field. Whereas in the case of the interfacial polarization, the mobility comes into picture, not even at very strong field, but at fairly low electric fields. So I would like to distinguish, if you are talking about space charge is nothing but the charges of the same kind accumulating in one spot or in a small region, and that would have an electric field. It would modify the applied electric field. This is the basis of all space charge calculations. So what is the region where the charges can accumulate, where their mobility is low? So once they are injected into the material, they stay put there, and the other charges of the same kind are coming in, and therefore it's one molecule will add up to several, and it will become a layer, and therefore it will provide you a source of an electric field that may add or subtract to the applied electric field, depending upon whether the charges are positive ions or a negative ion. And now that again can be resolved by applying an electric field which is varying in alternating field, and trying to figure out whether the positive charge layer is moving away or from the appropriate electrode. So if the electric field, if the calculations show that the internal field you have calculated is due to positive ions, then by applying the frequency, the way it moves towards the negative electrode will of course change. Higher the frequency, higher would be the mobility for that layer to move away. So from those experiments, you can try to figure out whether the space charge layer is due to positive ions or negative ions. Most probably it would not be due to the electron. The electron space charge occurs only at high electric field close to the high voltage electron.
We have one more question. Is there any reason to prefer TDS over FDS, time domain spectroscopy, over frequency domain spectroscopy?
Yes, TDS and FDS. Yeah, I think I just now answered. In the frequency domain spectroscopy, you measure the dielectric constant and the loss factor, not loss factor, but the epsilon double prime almost directly. You vary the frequency, and if it is digital, you would have one value gives the relative capacitance, and the other value gives the value of the epsilon double prime. There is the frequency domain spectrometry, and you would have a way of controlling the frequency. They used to be very expensive. I'm not sure what the price is now. So that is the frequency domain. The time domain spectroscopy, where you measure the current as a function of time. and with a applied field. The time domain spectroscopy, therefore, you cannot measure the current for smaller than 0.1 second, let us say, or 10 to the minus 2 seconds, the best you can do. So that is very low frequency. So the two experimental techniques are different. I could share an experience here when I was doing an experiment of time domain, measuring the current. I was measuring the current at a high temperature, and I removed the applied electric field, and the current still kept on increasing. The temperature was constant. There was no electric field because I had removed the electric field, and the current increased from 1 nanoampere, 10 to the minus 7, 1 microampere, at 1 milliampere. The sample suddenly broke down. I meant to investigate it further, but I got lost and I forgot to note down what sample I was studying, because we were doing experiment on a number of different samples. So that idea I could not pursue further because I had, out of carelessness, I had forgotten to note down what material I was investigating. So it is possible for you, if such a phenomenon is taking place, to a thermal breakdown. Once the breakdown has been initiated, it takes considerable time, a few minutes, and then the sample, the current you are measuring will have altogether a different value than the immediate value which the instrument shows.
We have another question. A dielectric consisting of an internal void, how to determine phenomenon inside and surrounding the void? That is the dominance of the charge polarity.
You can only arrive at it at the theory. There's no way you can make a measurement of the dielectric constant or the internal field, because any instrument you use, including an optical technique, if you like, in transparent materials, would alter the electric field itself. So when the measuring instrument interferes with the field you are trying to find, then that method would not be a satisfactory method. And this is the reason why the optical polarizability is so hard to determine. And mostly it is obtained by calculation from the known electron and electron distribution around the nucleus. So measurement is not a valuable proposition if you are trying to do things in a certain time frame.
I have a question from Dr. Ritesh Patel, who is an ex-student of IIT Kanpur. He wants to know sorry?
Excuse me, I would like to have a drink of water.
Sure, sure. We can break for 5 minutes if you like.
No, I am fine, actually. Yeah, okay.
Yeah, Ritesh would like to know what is the needs for measurements of polarization at low frequencies, very low frequencies. Why do we at all need to do that?
Because, that's a good question. I would like to think there are transients taking place at very low frequencies in power systems. Slowly varying transients, this is. Not the high frequency transients that arise when you open a circuit or close a circuit or things like that. But there are occasions when the frequency could be as low as 1 second or even several minutes. You'll see that the voltage in a power system having values higher than the operating value, but it's a very slowly increasing time. So if you wish to understand the behavior of your dielectric material when such transients occur, then you would like to know the behavior of the material at very low frequencies. But this slowly varying transient could be quite large, some cases not as large as the basic impulse level, but higher than the AC value, because it's neither AC or a DC. It's a very slowly varying component, and it could reach a value between 1 and 2 times the operating voltage of the insulation. In those cases, you would need to know what is the behavior at low frequencies.
Kingshuk, you're not audible. I've asked you to unmute yourself. You should be, yeah, now you're good. Yes.
Another question we have is, why does breakdown in air happens easily at higher frequencies?
Yes, it depends upon the electron motion within the material. Whether it is gas breakdown or a liquid breakdown, I'm not so sure about solids. Let us talk about the gas molecules, because the breakdown is mostly electron. The breakdown occurs due to the multiplication of electron within the volume. To get a discharge, you must reach a value of, say, 10 to the minus 4 amperes. And when the material is perfectly healthy, you would get a current less than 0.1 nanoamps. So how would this current of 0.1 nanoampere build up to the microamp or milliamp rate? This is due to the multiplication of the electrons. The multiplication occurs by collision. For collision, the electron must move to the positive electrode, and after 1 minute, the path it collides with a neutral molecule. Now, if within that time, so let us say you have a certain collision frequency, 10 to the 8 collisions per second. Now, when you apply the oscillating field, the electron will, after a few few mean field paths, it has not reached the other electrode, but now it is saying that the polarity has changed, so it must go to the opposite electrode. So it changes the direction of motion, and it would be moving to the positive electrode. And after a few minutes, 3 parts, it would have to change again, because the next half cycle, the polarity has changed. So within the bulk, between the two electrodes, the electron would be oscillating, and during each collision, after 4 or 5 mean free paths, it would generate more electrons at the same voltage. And therefore, we have a situation where the number of collisions increases with the frequency of the applied voltage. This is in the most probably in the region greater than the electron, which approaches the electron velocity 10 to the 7 centimeters per second, and therefore roughly about 10 to the 7 megahertz above, you would expect the frequency dependence of the breakdown voltage on the particular value of the frequency. This is why when you apply a few megahertz, the breakdown voltage is lower. It is lower than the DC or 50 hertz value. So we define a collision frequency by saying that there is an effective electric field, not the applied electric field. If you have applied an electric field which is a few gigahertz, then you have an effective electric field. And the effective electric field is the field you would apply without the frequency. What is the breakdown voltage, the ratio of the two. So without the frequency, the breakdown strength would be higher. So you will see the effective electric field, and you talk about a collision frequency in relation to the effective electric field. These experiments and these theories were developed particularly during the Second World War for the propagation of the radar signals, how the molecule behave for breakdown torque, how the electrons behave for the breakdown torque. And as I mentioned earlier, you can obtain the same information by applying a magnetic field where the electron would traverse a cycloidal path, and therefore more collision will occur. And depending upon the magnetic field, you would again define an effective electric field and try to calculate the collision frequency. And also the behavior changes, whether it is on the right-hand side or the left-hand side of the Paschen minimum, because on the left-hand side, breakdown occurs for longer path lengths rather than when compared with the other way around. So you would find if you are doing experiments below Paschen minimum, you will have to design your electrode such that the longer breakdown along the longer path would be avoided. Whereas on the high pressure side, you would try to make sure that breakdown at shorter lengths are avoided.
Kingshuk,
yes,
there is one last question that we will take from Nilesh.
Yeah.
And then we will close it down.
So Nilesh asks why high voltage conditioning or seasoning is required in vacuum chamber many times before test of impulse tests, or why in impulse test many times, especially in vacuum chamber, we change polarity to test at upper limit, many times need to apply particular polarity of voltage in states of, I think he should ask the question. Is he available there? Why in impulse test many times, especially in vacuum chamber, we change polarity to test at upper limit.
Yeah, let us answer that question,
Yeah.
that part. The breakdown in vacuum occurs because of field emission. The initial electrons are provided by the field emission. The field emission is that the projections, micro projections, the field would be 2 to 3 times the average field across the gap. Now, if it is 3 times the field, then there would be field emission from that point tip. These are microscopic projections. No matter how nicely you polish the electrode, there would still be micro projections. Now, the micro projections act as the source of electrons. And therefore, the breakdown will occur from these micro projections. Each time a spark occurs from a micro projection, the diameter of that micro projection become a bit large. It will become a slightly thicker projection, and therefore the electric field at that point would not be as high as before that spark. So this way, the electrodes are conditioned so that you are electrically removing as many as possible micro projections. And therefore, the breakdown voltage goes up because there are no more micro projections ready to initiate the breakdown. So this is called the conditioning process, of course. So you make 25 breakdown measurements, and you take only the last 10 of those, because the first 15 is probably due to the conditioning of the electrode. Now, with impulse voltage, it's of course a slightly different story. The impulse voltage, the breakdown mechanism itself may be slightly different. And depending upon which mechanism operates, during 1950s and 1960s, there was a waging war on between scientists, whether it's the Townsend mechanism or streamer mechanism taking place in gases, especially at atmospheric pressure. I belong to one group which said that the streamer mechanism takes place. My professor was Professor J. M. Meek. You might have heard his name. So the I should also mention in vacuum, in addition to the field emission, the occluded gases also play an important part in conditioning. And the gases which are occluded on the surface of the electrode, although there is vacuum. You see, in order to obtain vacuum, that is why you heat the entire equipment in an oven. You fix it around the equipment, and then we call it baking. You bake it at 300 degrees centigrade for 24 hours for the vacuum measurement to be made. Now that is because on the surface of the electrode, gases would be occluded. It's the gas pocket, and they come out only when the electrodes are heated. And you'll see during the baking process, the vacuum, if you want to get a vacuum which is lower than 10 to the minus 5 torr,
Yes.
if you want to measure bring down the vacuum lower than that, the diffusion pump itself will not do it. The diffusion pump can only bring it down from 10 to the minus 3 to at most 10 to the minus 6. But to conduct experiments under vacuum, you need to have a vacuum as good as 10 to the minus 10 torr. So to cover that range, you need to bake the equipment because you need to drive out these occluded gases. And that's also one reason why in vacuum breakdown, your vacuum may not be good enough in order to avoid the conditioning effect.
Thanks a lot, sir. I don't think there are any more questions with us. It was excellent to hear your expert answers to those questions. Ma'am, you can.
Yeah, thank you, Professor Raju, for giving us such a brilliant interaction session. We learned many things about high voltage from you, about dielectrics from you today, but I think we have learned a much more important lesson. I don't think many of us are capable of waking up at sub-zero temperatures and be ready at 6:30 a.m. in the morning to answer questions from random strangers, just to share the knowledge that you have and for no other good reason. This is a very important lesson. And actually the moment my students saw you on board, we were expecting you later. The moment my students saw you on board, that's the first thing they say, that what kind of commitment is this? I think this is the most important lesson we take from you today. Thank you very much for being with us. Well, it was a great pleasure and great honor.
Thank you very much. I appreciate this opportunity. I enjoy talking to young students, because whenever I see a young student, I say to myself, well, I was one of you there at some time. And so it gives me an opportunity to brush up and also convince myself I am still capable of talking some sense on these subjects. So thank you very much. And all the students, I thank you and best of luck in your career. As I said, Professor Gupta is the ablest. I can again narrate an incident. I am sorry I keep going back. You might have heard the name of Loeb, who was professor of physics at the California Institute of Technology. And he visited Liverpool, where I was a graduate students. And while we were discussing ionization, he said, oh, there is an equation for current for Townsend. I forget the name. And he was only 64, 65 years old at that time. So I always look for an opportunity to keep up to date. And thank you for providing me this opportunity. Thank you so much. And
it was our pleasure, sir.